Something out there is quietly shaping stars in ways we're only beginning to notice. It happens far beyond the reach of telescopes, yet its effects appear in real data, from unusual light patterns to unexpected chemical signatures. This is where rare stars challenge what we think we know. Welcome to Relaxing Facts Studio, where we follow those signals step by step, using observable science and measured evidence. In the next few minutes, each discovery connects to a larger system, revealing how the universe builds, transforms, and sometimes breaks its own rules in ways scientists are still working to understand. Galaxies in our region are not drifting randomly through space. They are moving in a shared direction towards something we cannot directly see. This motion shows up in velocity maps, where thousands of galaxies shift relative to the cosmic microwave background, forming a pattern called large-scale bulk flow. The effect points toward a hidden mass concentration known as the Great Attractor. It sits behind dense regions of our own galaxy, and its pull extends across hundreds of millions of light years. That hidden region remains difficult to observe because thick dust and stars block our view along the Milky Way's plane, creating what astronomers call the zone of avoidance. Light from distant objects gets scattered and absorbed before reaching telescopes. But the motion of galaxies still reveals what lies beyond. Scientists reconstruct the mass distribution indirectly using gravitational flow mapping and redshift surveys. The structure is inferred, not seen directly. Yet the data consistently points to a massive gravitational anchor. That gravitational pull does more than move entire galaxies. It also influences the paths of ancient star clusters traveling through intergalactic space. Some globular clusters, which are tightly bound systems of up to 1 million stars, can be displaced during galaxy interactions and tidal stripping events. Over millions of years, these clusters follow curved trajectories shaped by surrounding mass distributions. Their structure holds together despite extreme distances, and their motion becomes part of a larger cosmic flow. That larger flow is not controlled by a single force but by a balance between competing regions of attraction and repulsion across the cosmic web. Massive clusters pull matter inward, while vast underdense regions, sometimes called cosmic voids, push matter away through gravitational gradients. This interaction forms a network of motion across superclusters. The result is a dynamic system where galaxies, clusters, and even isolated stars gradually shift position. And over billions of years, this flow continues to reshape the large-scale structure of the universe. Two ultra-dense stars spiral toward each other, moving faster with every orbit until they collide in a fraction of a second. This final plunge releases energy detectable across the universe as gravitational waves, ripples in space-time first measured in 2017. Each star is a neutron star, where matter is compressed so tightly that a teaspoon would weigh billions of tons. The system loses orbital energy as radiation, and the collision becomes one of the most extreme events ever observed. That collision does not end quietly. It triggers a brief, powerful explosion known as a kilonova. In less than a day, expanding plasma ejects material at a significant fraction of the speed of light, forming a rapidly fading glow. The light curve changes color as heavy elements form and decay, shifting from blue to red within days. This emission is short-lived, and it is one of the few direct signals scientists can track from these rare events. That expanding material carries something unusual: conditions intense enough to build elements heavier than iron through rapid neutron capture, known as the R process. In this environment, atomic nuclei absorb neutrons faster than they can decay, forming unstable isotopes that quickly transform into stable heavy elements. Gold, platinum, and uranium emerge from this sequence. The process happens in seconds, and it produces more heavy elements than typical stars can generate in millions of years. That newly formed material does not remain isolated. It spreads into surrounding space and becomes part of future star systems. Over time, these elements mix into interstellar gas clouds, eventually forming new stars and planets. Meteorite analysis on Earth shows traces of this origin through isotopic signatures linked to ancient neutron star mergers. The gold in everyday objects likely formed this way, and its presence connects planetary matter to some of the most violent collisions in the universe. Two nearby stars can end up sharing matter instead of staying separate, and the transfer begins when one expands beyond its stable boundary. This boundary is called the Roche lobe, and once gas crosses it, gravity pulls material toward the companion star. The flow forms a stream of plasma moving across space, and over time, one star gains mass while the other slowly loses it. That incoming material does not fall straight in. It spreads into a rotating structure called an accretion disk. Friction within the disk heats the gas to millions of degrees, producing strong X-ray emissions that telescopes can detect across the galaxy. The energy output can exceed that of normal stars, and the system becomes one of the brightest high-energy sources in its region. That intense interaction also changes the chemical makeup of surrounding space, because the transferred material can undergo nuclear processing under extreme pressure and temperature. Some systems produce unusual isotopes not commonly formed in isolated stars. Stellar winds and eruptions then push this enriched material outward. The process affects nearby gas clouds, and it contributes to the evolving chemistry of the galaxy. That gradual mass exchange eventually leads to unstable outcomes, depending on how much material is transferred and how fast. A white dwarf gaining mass may approach the Chandrasekhar limit, triggering a Type Ia supernova. Other systems collapse into neutron stars or disrupt their orbits entirely. These endpoints reshape local space, and they leave behind compact remnants that continue influencing their surroundings. Some planets form in regions where carbon is more abundant than oxygen, changing how solid material builds from the start. In these protoplanetary disks, carbon compounds condense into graphite and other dense forms instead of silicate rock. Over time, collisions and pressure turn these materials into compact planetary bodies. The chemistry shifts the entire formation pathway, and the result can be a world dominated by carbon-rich minerals. That carbon-rich structure does not stay in its original form. Increasing pressure deep inside the planet transforms it into diamond. Under extreme compression, carbon atoms rearrange into a tightly bonded crystal lattice, creating layers that may extend for thousands of miles. The process depends on gravity and internal pressure gradients. And on larger super-Earths, the effect becomes even more pronounced. That diamond interior changes how heat moves through the planet, because diamond conducts thermal energy far more efficiently than typical rock. Heat from the core can travel outward with less resistance, stabilizing internal temperature differences over long timescales. This steady transfer may produce a faint internal glow, and it can affect how the planet cools over billions of years. That stable heat flow also influences the planet's surface and atmosphere, where carbon-based weather systems may operate under unfamiliar conditions. In some models, high-pressure atmospheres allow carbon to condense and fall as solid particles, sometimes described as diamond dust. The surface could reflect light in unusual ways, and the entire planet might appear dimly luminous against the darkness of space. A dense stellar core can end up buried inside a much larger star, creating an object that behaves unlike anything in standard models. This happens when a neutron star spirals into a red supergiant during a close binary interaction and becomes trapped at its center. The outer layers remain extended and cool, but the core is something far more extreme. That extreme core does not produce energy the usual way. Instead of normal fusion shells, matter falls directly onto the neutron star's surface and releases energy through rapid accretion. The process alters how heat moves outward, replacing convection patterns with more complex transport mechanisms. The structure becomes unstable to model precisely, and small changes in input conditions can shift the outcome. That unusual internal process leaves a detectable signature at the surface, because certain elements become overproduced and rise through the outer layers. Observations show enhanced levels of elements like rubidium and molybdenum in candidate stars. These patterns do not match typical stellar evolution pathways, and they provide one of the few ways to identify such objects. That identification remains uncertain, because these stars resemble ordinary red supergiants in most observable features. One well-known candidate, HV 2112, shows some expected chemical anomalies but not all predicted signals. Spectral data can be difficult to interpret due to atmospheric effects, and current evidence does not fully confirm or rule out their existence. Some stars contain almost no heavy elements, and their composition reflects conditions from the early universe. These low metallicity stars formed before repeated cycles of stellar enrichment, preserving a simpler chemical mix dominated by hydrogen and helium. Their atmospheres act like time capsules, and they provide direct evidence of how the first stellar systems evolved. That preserved composition records past explosions, because traces of heavier elements appear in specific ratios linked to ancient supernova events. By analyzing spectral lines, scientists identify patterns consistent with rapid neutron capture, known as the R process. These signatures reveal the type and energy of the original explosions, and they help classify events that occurred billions of years ago. That classification allows researchers to reconstruct how the Milky Way formed, using stellar motion and chemical tagging to group stars with shared origins. Orbital paths show whether stars formed locally or were captured from smaller galaxies. Combined with composition data, this method builds a timeline of galactic assembly. And it turns individual stars into markers of large-scale history. That history also sets limits on where planets can form, because heavier elements are required to build solid surfaces. Stars with extremely low metallicity are less likely to host rocky planets like Earth. This creates a threshold in cosmic evolution, and it helps explain when and where habitable environments could first appear. A star can suddenly ignite a new fuel deep in its core after exhausting hydrogen, and the change happens rapidly under extreme conditions. As the core contracts, temperature rises until helium fusion begins in a runaway event known as the helium flash. Energy release increases sharply, and the star's internal structure reorganizes within a short timescale. That ignition does more than stabilize the core. It creates new elements through a process where helium nuclei combine to form heavier atoms. This sequence, called the triple alpha process, produces carbon and later oxygen under sustained high temperatures. These elements are essential for complex chemistry, and they form the basis for many materials found in planets. That internal production does not remain locked inside the star, because strong stellar winds can carry newly formed elements into surrounding space. Layers of gas are gradually expelled, enriching the interstellar medium with carbon and oxygen. This material mixes into future star-forming regions, and it changes the composition of new stellar systems. That enrichment feeds back into galaxy evolution, because the presence of heavier elements affects how gas clouds cool and collapse to form stars. Regions with higher metallicity can form stars more efficiently under certain conditions. This influences star formation rates over time, and it helps regulate how galaxies grow and change across billions of years. Some stellar remnants continue changing long after they stop producing light, slowly cooling over timescales far beyond the current age of the universe. White dwarfs, which are dense cores left behind after stars like the Sun shed their outer layers, gradually lose heat and become more stable. Their atoms settle into tightly packed states, and over trillions of years, they approach a near-uniform internal structure. That long-term stability leads to a theoretical transformation, where nuclear reactions and quantum processes could rearrange matter into iron-like compositions. Iron represents one of the most stable nuclear configurations, minimizing energy at the atomic level. This process is extremely slow and not directly observed, and it depends on conditions that exist only over unimaginable durations. That gradual evolution occurs within a larger cosmic trend, where the universe itself moves toward thermal equilibrium as stars burn out and energy differences fade. This state is often described as heat death, where usable energy becomes scarce and large-scale processes slow down. Temperature differences shrink across space, and fewer interactions can produce meaningful change. That decline may extend even further if fundamental particles are not perfectly stable, because some theories suggest protons could decay over extremely long timescales. If that happens, matter itself would gradually break down into lighter particles and radiation. Structures would dissolve, and the universe would approach a state where only the simplest forms of energy remain. Stars normally appear round because gravity pulls matter evenly toward the center, smoothing out irregularities over time. This balance creates a shape known as hydrostatic equilibrium, where inward gravitational force matches outward pressure from hot plasma. Any distortion tends to collapse quickly, and most stars maintain a near-perfect sphere throughout their lifetimes. That symmetry can break under extreme conditions, especially when magnetic fields become strong enough to influence the movement of charged particles. In certain compact stars, like magnetars, magnetic pressure can compete with gravity and distort the outer layers. Plasma follows field lines instead of spreading evenly, and the surface may develop uneven or angular features. That deformation is not random. Internal oscillations can create standing wave patterns that shape how matter distributes across the star. These vibrations, sometimes called starquakes, produce nodes where motion cancels out and regions where it intensifies. The pattern depends on density and rotation, and it can introduce geometric structure into an otherwise fluid object. That structure leads to theoretical models where stars might briefly exhibit symmetrical patterns resembling cubes or octahedrons under specific conditions. These shapes are not solid edges but regions of varying density and brightness. Observing them directly remains difficult with current instruments, and their existence is still being tested through indirect measurements and simulations. Across all these rare stars and distant systems, one pattern stays clear. The universe is constantly building, reshaping, and sometimes breaking its own rules in ways we are still learning to measure. If you've made it this far, thank you for watching Relaxing Facts Studio. Your support keeps this work alive and growing. If you haven't subscribed yet, this is a great moment to join the channel. Share this episode on your social media, like the video to help it reach more viewers, and leave a comment with your thoughts. Every interaction truly helps the channel continue producing these explorations.